In today's lesson, we're going to talk about adding and subtracting matrices. We're also going to talk about scalar multiplication of a matrix. So our goal then, our objective, is to find the sums and differences of matrices, and then to find the product of a scalar and a matrix. According to our textbook, the sum of matrices having the same dimensions is the matrix whose elements are the sums of the corresponding elements of the matrices being added. We might want to think of this strategy instead. Two things need to be true about those matrices in order to add or subtract them. First is they must have the same dimensions. Secondly, after we establish they have the same dimensions, we would add or subtract corresponding elements. Those would be the elements that are in the same position in both matrices. So for example, in this case, we're asked to add two matrices, and this has the same dimensions. Both of these matrices have the same dimensions. They both have 3 rows and 2 columns. They're both 3 by 2 matrices, and therefore we would add the elements in the corresponding position. So 3 is in row 1, column 1, and so is -6 in the other matrix. So let's take a look at what that would look like if we combine them. So we're going to take the 3 and the -6, add them together because they're both in row 1, column 1, and we'll put that result in that same spot. Then we'll take the -2 and add it to the +4, which are row 1, column 2 of each, and put that in the row 1, column 2 of my resulting matrix. And then the 1 plus the 0 is in row 2, column 1, the 0 plus the -9, row 2, column 2, the -5 plus the 3 in row 3, column 1, and the 7 plus the 0 in row 3, column 2. And when we simplify that, 3 plus -6 is -3, -2 plus 4 is 2, 1 plus 0 is 1, 0 plus -9 is -9, -5 plus 3 is -2, and 7 plus 0 is 7, and that would be the result of adding these two particular matrices. Again, two things would have to be true. They have to have the same dimensions, and then we would add the elements in the corresponding positions. Well, what if they don't have the same dimensions? Well, if they don't have the same dimensions, they don't have corresponding elements in all of the same positions, and therefore matrix addition or subtraction is not defined. We want to talk about another special kind of matrix. We talked about this before. It's the identity for addition, or we call it the zero matrix. So for any matrix that has m by n elements in its matrix, 0 mn is the identity for addition. So for instance, if I had two 2 by 2 matrices, one we're going to call A, 2 rows, 2 columns. We're going to add to that the 0 matrix, which is also 2 rows and 2 columns. So we want to take the matrix A, B, C, D, add it to the 0 matrix 0, 0, 0, 0. And so we add the elements in each corresponding positions: A plus 0, B plus 0, C plus 0, D plus 0. And of course, adding anything to each element is not going to change it. So A plus 0 is A, B plus 0 is B, C plus 0 is still C, D plus 0 is still D, and therefore we have the additive identity. So just like adding 0 to any number, that number does not change. Same thing is true for adding a 0 matrix to any other matrix. Other thing we want to talk about is the additive inverse. Now, before matrices, those would be two numbers you would add together to get 0, like 5 and -5. And so here's our notation. If we denote our matrix as A, then we would talk about its additive inverse by putting a minus sign in front of it. And the definition of that is each element in our additive inverse would be the opposite of the corresponding element in our original matrix. So for example, if we are looking at matrix A, and that contains the elements 1, 2, 3, 4, then the additive inverse would have the inverse or the opposites of each element. So instead of 1, -1, instead of 2, -2, instead of 3, -3, and instead of 4, -4 in their corresponding positions. And then if you add two matrices that are inverses of each other, that gives you the additive identity we just talked about before, which is a zero matrix. So 1 plus negative 1 is 0, 2 plus negative 2 is 0, 3 plus negative 3 is 0, 4 plus negative 4 is 0. That would give us that additive identity. All right, let's subtract two matrices. So we have matrix A is 1, 6, negative 8, 2. Matrix B happens to be 4, negative 2, and then 3 and 7. To subtract them, don't forget that what we've talked about all year long is that subtracting is the same as adding the inverse or the additive inverse or the opposite, we may have called it. And so instead of subtracting, let's kind of distribute out, so to speak, this minus sign to each element in this 2 by 2 matrix. So that becomes a negative 4, a positive 2. Take the opposite of each one. That would become a negative 3, and that would become a negative 7. And then we can add those two matrices just like we did in the previous example. 1 plus negative 4 is negative 3. 6 plus 2 is 8. Negative 8 plus negative 3 is negative 11. And 2 plus negative 7 is negative 5. So when we are asked to subtract two matrices, you can just add the inverse instead. All right, let's take a look at our next example. If matrix A is the matrix containing the elements 2, 0, 5, negative 7, find 3 times matrix A. And this is called the scalar multiplication. Essentially, we are multiplying each element in that matrix by the constant. In this case, it's the number 3. So let's do that. We're going to take 3 times the 2, 3 times the 0, 3 times the 5, and 3 times the negative 7. Each element in that matrix gets multiplied by that number 3. And then let's just simplify that off. 3 times 2 is 6, 3 times 0 is 0, 3 times 5 is 15, and then 3 times negative 7 is negative 21. All right, and then if we have an equation where a variable represents a matrix, we call this a matrix equation. And a matrix equation can be solved using what we've just learned, matrix addition or subtraction, and then scalar multiplication. So let's take a look at an example. We're going to solve for the matrix for x. So we have 2 times x plus 2 times the matrix containing the elements 1, negative 2, 0, 3. That's equal to 8 times the matrix containing the elements 1 half, 0, negative 1, 1/4. So let's begin the process of simplifying by doing that scalar multiplication. And in this case, we're going to take this 2 by 2 matrix and multiply everything by that constant 2. 2 times 1 is 2. 2 times negative 2 is negative 4. 2 times 0 is 0. 2 times 3 is 6. Same thing on the right side of the equal sign. We're going to multiply everything by the 8. 8 times a half of 8 is 4. 8 times 0 is 0. 8 times negative 1 is negative 8. And 8 times 1/4 is 2. In our next step, we want to try to isolate the variable, as always, get x by itself. So that means we need to subtract the matrix that is being added to it. So to do so, we are going to get 2x by itself by subtracting our matrix, which contains the elements 2, negative 4, 0, 6, from both sides of the equation. And that isolates 2 times x. So again, we can do the subtraction. We do add the additive inverse instead. So distribute out that negative, so to speak, to each term in the second matrix. That'll become a negative 2. The inverse of negative 4 is positive 4. Still have 0, and then we have negative 6. Let's add those two matrices together. So I didn't write out the step where we said 4 plus negative 2 is 2. 0 plus 4 is 4. Negative 8 plus 0 is negative 8. And 2 plus negative 6 is negative 4. All right, the last thing in our pursuit of finding out what the matrix X represents is that is being multiplied by 2, so we would need to divide or multiply by its reciprocal. So if we multiplied both sides of this equation by the reciprocal of 2, which is a half, that would give us x by itself on the left side of the equation. And then we have our scalar multiplication to do. We want to take 1/2 times every element in this matrix. And let's do that. 1/2 of 2 is 1. 1/2 of 4 is 2. 1/2 of -8 is -4. 1/2 of -4 is -2. So the matrix we were looking for, X, is represented by this 2 by 2 matrix containing the elements 1, 2, -4, -2. All right, to recap today's goals very quickly, we wanted to learn a couple of things. One, to add or subtract matrices, and then do scalar multiplication. And then we wanted to use those two ideas together to solve an equation to find, in this case, the missing matrix X. And that concludes today's lesson.